Okay, so just to clarify, just distinguish, we talk about absolute maximum, absolute minimum, maximum or minimum at an endpoint. Our local maximum and our local minimum really refer to our stationary points, okay? Not necessarily the overall maximum of the graph. So for example, I might have that graph there. So at this point here, it's what we call a local max, because in that isolated area, that's the maximum of the function, and we know by definition a local max refers to a stationary point or returning point. The actual maximum of the function would be out here somewhere, because all of these values are greater than that maximum value there. In the same way, this point here is a local minimum, because everything down here is actually smaller than the function. So my stationary points aren't necessarily the smallest or the largest values of the function. They're just the local smallest or largest. If we want to know the actual largest or smallest, we refer to it as the absolute maximum or the absolute minimum. All right? So if we maybe rub out all that stuff there, and let's have a look at our graph where we've got a function that's defined over a particular domain, and we want to find out the absolute minimum value of the function. All right? So whenever we want to do an absolute, really, we need to do a graph. There's my graph, and we've got x squared plus 2, which is up here somewhere. So that's the whole graph. And we're interested in the graph between -2 and 4. So in reality, I've got to reduce this. It's maybe to look a bit like that. So at that point there, x is equal to -2. At that point here, x is equal to 4. So I can see straight away, without necessarily even finding a derivative, my minimum value there is at 0.2. This value here at x equal to 4, if I substitute it into the function, f of 4 is 4 squared plus 2, which is 18. So that's the point 418. And this point here is the point -2, well, -2 squared is 4 plus 2, which is 6. So they're the key points. So the absolute maximum, and we can see, is equal to 18. The absolute minimum is, well, the smallest value of the function is 2, isn't it? Which means in reality, that's the information we need for our range. My range is from 2 to 18, and just to confirm, my domain is from -2 to 4. So I guess the key point there is my range isn't necessarily the values of the function at the endpoints. So that at the endpoint, the y value is 6 and 18, but the absolute minimum is at point 0.2. All right, we've got the graph of a graph restricted on the domain of -2 to 1. Again, find the maximum minimum values of the function. Again, absolutely normally we would go through finding some derivatives, but because we've got some graphs here that we should really know what they look like. There's a cubic graph with a point of inflection. That's the full cubic graph. I want to restrict it between -2 and 1. So let's work out f of -2. -2 cubed plus 2, which is -8 plus 2, which equals -6. So maybe let's restrict our graph, say there. So there's -2, and that's the point -2, -6. The other point is at x equal to 1. So if I put 1 in there. F of 1 is equal to 1 cubed plus 2, which is equal to 3. So my other points, at x equal to 1 is the point 1, 3, and that's my point of inflection. Find the maximum minimum value of the function. So clearly we can see the maximum is 3, the minimum is equal to -6. Let's just refresh example 12 to graph 15 on 27. All right. In example 12, the maximum volume of the box was found. The maximum value corresponded to a local maximum of the graph of blah, blah, blah. This was also the absolute maximum value. If the height of the box must be less than 0.3 metres, what will the maximum volume of the box be? So, if we remember, if we sketch the graph, something like that, and then it would have gone up like that, all right? And the actual maximum, so the maximum value there was at 1/3, 6 on 27. So we need the height of our box. So this is x, and this is v. All right, so don't forget, from that previous example, there was a relationship between the... So at the moment, if we have a look at our coordinates for the maximum, my height is equal to 1/3, and the volume is equal to 6 on 27. Now, obviously 1/3 is 0.333. So it says that my height has to be less than 0.3. So that means that my height here, the x value, has to stop here at 0.3 somewhere. Okay, so clearly my maximum is actually going to occur. So since the height is less than 0.3, the maximum, we're saying less than or equal to, the maximum occurs at v of 0.3. In other words, if I substitute 0.3 into that rule, 4 times 0.3 cubed minus 8 times 0.3 squared, 4 times 0.3, and that's equal to 0.588, which is actually 147 on 250. Okay, so it's just really being clear in your head about an absolute maximum or a maximum value if we have some constraints placed upon us. All right, off you go. So when we talk about kinematics, we really talk about the motion of a particle, the movement of a particle, okay, from a particular fixed point. And we talk about straight line motion. All right, so the key attributes, if you like, of kinematics is the particle's moving in a straight line, okay, and the position is determined by its distance from the origin, all right? So if it's to the left of the origin, typically we have a negative distance. If it's to the right of the origin, we have a positive distance. All right, so the key things are displacement is the change in position, all right? So where is it at the end? However, the distance is how far we actually travel. All right, so for example, if I travel from home to school at St Bernard's, which is about 30 k's from my home, and then I travel back home again, my displacement is 0. The distance I've travelled is the 30 plus 30, which is 60 kilometres. All right, so let's have a bit of a look. A particle moves in a straight line, so its position is given by x equals that. Find its initial position. So the initial anything means t is equal to 0. So at t equal to 0, x of 0 is equal to 0 squared minus 7 times 0 plus 6, which is 6, what have we got, centimetres. So we're starting 6 centimetres to the right of the origin. At t equal to 4, my position is 4 squared minus 7 times 4 plus 6, which is 16 minus 28 plus 6, which is 22, which is negative 6 centimetres. So over that 4-second period, the distance I've travelled is more than likely the 6 centimetres where I was to the negative 6 centimetres that. So I've travelled 12 centimetres, but my displacement from the origin is 6 centimetres. Okay? Let's talk about some other terms. So there's my displacement. My velocity, or my average velocity, is the change in the displacement over the change in time. So notice that it's the change in displacement, which means where I finished to where I started over the time it's taken me to do that. The instantaneous average velocity, instantaneous velocity is dx dt, the derivative of my position. All right? So remember, the gradient is the rise over the run, and in a position time graph, the gradient is the change in position over the change in time. So that's my average. The derivative of that is the gradient of that graph, which is also the instantaneous velocity. So typically our units of velocity, metres per second, kilometres per hour, all those sorts of things. So let's go back to our question that we've been looking at. So very quickly, so my velocity is given by, I hate it when I do that. The velocity is, the rule for my velocity is given as 2t minus 7, the derivative of that equation. All right? So the initial velocity is the velocity at 0, which is negative 7 centimetres per second. So in other words, if there's my axis and I'm starting from memory out here at 6, or actually up there at 6, well then I'm heading towards, in some way, shape or form, there may not be a straight line, I'm heading back towards the origin. So the gradient there is negative, and in fact it's negative 7 centimetres, okay, at the start. When does the velocity equal 0? So velocity equal to 0, we can obviously solve that equation equal to 0. 2t minus 7 is equal to 0. 2t is equal to 7. T is equal to 7 on 2. And where am I when that happens? So at t equal to 2, x is equal to 7 on 2 squared minus 7 times 7 on 2 plus 6, which is equal to 49 on 4 minus 49 on 2 plus, let's make that on 4, 24 on 4. So that becomes negative 98 on 4, so negative 49 on 4 plus 24 on 4, negative 25 on 4. So what does that mean? That's where I am, okay, when the velocity is 0, or when my turning point occurs. Average velocity, okay, is about where I am at the start, where I am at the finish, how long has it taken me there to get there. So my position at the start, we decided was 6. My position 4 seconds later is equal to 16 minus 28 plus 6, which is negative 6. So the average velocity is equal to minus 6 minus 6 over 4 minus 0, which is negative 3 centimetres per second. So that's my average velocity. My average speed, on the other hand, we really do need to sketch our graph. So we know that t squared minus 7t, so t squared minus 7t plus 6, if I factorise that, t minus 6, t minus 1. So I've got 1 and 6 are my intercepts. My turning point was at 7 on 2, which is about there, and I started at 6. So the graph looks a bit like that. Alright, so now don't forget that this doesn't mean that my particle was travelling down a hill. What it means is that at 0 seconds, I was 6 centimetres in a positive direction. As it turns out, 1 second later, I've got back to the origin. And then my turning point is at the point, let me say it was 7 on 2, negative 25 on 4. Yeah? So that means after 3.5 seconds, I'm down here at negative 25 on 4 metres. And then half a second later, at t equal to 4, I was at negative 6 metres. So what I want to do now, to work out my average speed, I need the total distance I've travelled. Total distance over total time. So the time's easy. I was travelling for 4 seconds. But the distance, well, for the first 3.5 seconds, I got through that section of the curve. Okay, so, and that's a total of 6 centimetres plus another 6.25 centimetres. So that yellow length of the line, that's 12.25 centimetres. Now, in the next half a second, I travelled back to there at negative 6. So that little section there, I went from negative 6.25 to negative 6, which means I travelled 1/4 of a centimetre. So the total distance I travelled, if I add them together, is 12.5 centimetres. Yeah? So if I wanted to divide 12.5 by 4, I'm going to get 3.125 centimetres per second is my average speed. All right? So 2 really big key terms in there. If I talk about the speed, I'm talking about a total distance. If I'm talking about a velocity, I'm talking about the displacement. All right, so where I was, where I started, how long it's taken me for it to happen. All right. The last of these things that we need to look at is our acceleration. And the acceleration, in the same way that the velocity is the change in distance over the change in time, my acceleration is the change in velocity over the change in time. You know, people talk about, oh, my car goes from 0 to 100 in 10 seconds. So that's talking about the acceleration of the car, all right? Again, average acceleration, what it was at the end, what it is at the start, the difference. Instantaneous acceleration is the derivative of my velocity equation, all right? Little thing, zero acceleration means the particle is moving at the constant velocity. I'm sitting on exactly 60 kilometres an hour. I'm not accelerating, I'm not decelerating, I'm just on that same speed or that same velocity.